Hey folks, I hope you're doing well. This is a short video about Riemann sums in which we introduce the motivating question for Calculus 2. That is the question that sort of leads to the integral, and Calculus 2 is fairly described as integral calculus. For comparison, Calculus 1 is differential calculus. It's the calculus of the derivative. And the sort of question that leads to the derivative is what's the slope of a curve? And you've all had calculus 1, so you know how that story goes. The problem in calculus 2 has to do with area. So let's start with some easy area, namely some areas we know. The basic area that we know is the area of a rectangle, the figure on the left-hand side. The area of a rectangle is length times width, and with the little grid on the blue rectangle, you can see why that is. If a rectangle is 5 units wide and 3 units high, then we can divide it into 15 squares of unit area, and hence 15 square units, 3 times 5. So this area makes perfectly good sense. The area of a triangle, well, a triangle is kind of half a rectangle, at least, a certain kind of triangle. And so its area should be 1/2 of the length times width, and we usually call those things base and height when we're talking about a triangle. So these are the kinds of areas that we know how to compute. Now there are other areas that you know how to compute, but I will point out that some of them, in fact, the one that may jump to mind is the area of a circle. While you know the formula for it, I'm not sure that you know where it comes from or why it works, right? Here, these formulas make perfectly good sense based on the picture. But why is the area of a circle pi times the radius squared? That's probably the best answer you have through no fault of your own, is because someone told you that's what the area of a circle is. More on that later, but for now, I'm going to point out that we know how to find areas of things that have straight sides, roughly speaking. Even if it's more complicated than a rectangle or a triangle, like say a pentagon here, this 5-sided figure, what I could do is I could cut this up into a bunch of triangles, and since I know how to find the area of a triangle, I could take my ruler out and figure out what the area of the pentagon is. And even if this were a really complicated figure, as long as the sides are straight, I can cut it up into rectangles and triangles and figure out the area from the area of pieces. What is hard, I would say, however, is a region that has curved sides like this. We don't have a good formula for this. Again, the area of a circle is kind of an exception, but that's a mysterious formula, and it's not clear I could cut this into circles in any event. Okay, so how are we going to solve this problem? How are we going to find the area of a curved region? Well, the first thing we're going to do is actually consider a simpler problem than this. So we won't consider just any old kind of curvy region, but rather we'll take a region that has 3 straight sides and 1 curvy side, because this makes it fairly straightforward to embed the region in the xy plane, right? What we'll do is we'll put one side along the x-axis, and then one side will be at some x value, we'll usually call that A, and another side will be at another x value, we'll call that B. Those are the 3 straight sides, and then we'll let the kind of top side be curvy. Now, the orientation doesn't really matter because the area is the same whether the curve is on top or on the bottom or on the left or on the right. So we may as well consider the curve on the top as we are in this picture. One advantage to this is we can describe that top curve using a function, right? We can just say it's the graph of some function. We know lots and lots of different functions. So already we can generate all kinds of different curvy regions where we mean really one-side curvy regions. Nonetheless, this is still a hard problem. I don't know how to figure out an area that has this sort of odd shape. So here's a specific example. Let's take a specific function, y equals x squared plus 1, and a specific interval, 0, 2, right? So instead of the abstract f of x and a and b, and so if I reproduce the above picture, this kind of picture, but with this example, this is what the picture looks like, right? So this blue curve is the graph of the parabola y equals x squared plus 1. You can see the left end point over here is at x equals 0. The right end point is at x equals 2. Okay, so we're trying to figure out this blue area. And again, this is a new problem. This isn't a rectangle or a triangle. I don't have any kind of formula for this. So how are we going to come up with the area? Well, our strategy mirrors the strategy you used in Calculus 1 to find the slope of the curve. And that is, we don't actually try to compute the area. Rather, we try to approximate the area. And we try to approximate the area in a smart way. What I mean by a smart way is I want my approximations to be as easy to calculate as possible, and crucially, I want them to be improvable. Okay, so let's start just with some sort of very crude estimates of this area. Probably the simplest way to estimate the area of the blue region is to use a box. That is, just put a rectangle around it. And there are actually lots of different ways that you could do that. You could put like a black rectangle kind of around the whole picture. And this black rectangle on the right, that's clearly too big, right? The blue area is smaller. But it is easy to compute the area of the box. The width is 2, the height's 5, so the area is 10. So 10 is a very crude estimate and clearly an overestimate. Or we could draw a box that's too small, right? Say we put a box that's inside the blue area instead of over the top of it. Again, it's easy to compute the area of the box. It's 2 by 1, so its area is 2. And so I get a crude underestimate of 2. Now, this doesn't seem terribly useful. We're way off in both cases. However, a key observation here is that if the interval were narrower, we wouldn't be off by as much. For example, suppose that instead of going from 0 to 2, the interval just went from 1.5 to 2. Well, here's a picture of what the sort of put a box around it approximation looks like. It's still too big, it's still off, but it doesn't look as bad as it does up here. If the interval went just from 1.9 to 2, that's the right-hand image over here, again, now our put a box around it strategy actually looks pretty good. We're only off by this tiny little corner up here in the upper left. So this is not a real sophisticated strategy, put a box around it. And it doesn't work well on a wide interval, but it does seem to work pretty well on a narrow interval. So this gives us an idea. We're going to take our original region, this one, and we'll cut it into a lot of really skinny strips. And on each strip, we'll use the put a box around it idea to approximate. So here's an example. Here I've taken the original picture and I've cut it into 2 vertical strips. And you can see we do that evenly, right? The interval goes from 0 to 2, so we cut it exactly in half. And on each half, I put a box around the curve. And I can compute the areas of the boxes, right? The left-hand box is 1 by 2, and the right-hand box is 1 by 5. So 2 plus 5 is 7, and I get an estimate that's better than the estimate before, right? The estimate up here, 10, included a lot of extra area in the upper left that's not there anymore in our new estimate. If we cut it into 4 pieces instead of 2 pieces, things look even better. Again, this is very much a visual argument, but so far things are at least looking good. Again, I take the original interval from 0 to 2, I split it into 4 equal pieces, and on each piece, I put a box around it. And then I just tally up the areas of all the boxes, and I'll leave it to you to check the math here, that comes out to 5.75. And our estimates look like they're getting better. Okay, a little bit of notation for this kind of approximation. We will use this notation, which looks complicated, but is not so bad once we unpack the pieces. First of all, notice that I have adopted the strategy of putting a box around the region instead of putting a box underneath the region. That's kind of an arbitrary choice. There's no reason to think that one is necessarily better than the other. Notice that what we're really doing here is on the right in this picture, I'm drawing the top of the box using the function value at the right endpoint of the interval. Whereas on the left, I'm drawing the top of the box using the function value at the left endpoint of the interval. We'll call this kind of approximation a right Riemann sum, or a right-hand approximation, and we'll call this kind of approximation a left-hand approximation. So down here in this picture, This is a right-hand approximation because on each interval, I'm using the function value at the right end to draw the top of the box. That's where the R comes from. R is for right, L is for left. The subscript is the number of rectangles or the number of subintervals. Clearly there's 1, 2, 3, 4, so this is R sub 4. And then I need a couple of other pieces of information to tell me what's going on. What function are you using? What function are you trying to estimate the area under, and what function are you using to draw the box tops? Well, our function is f of x equals x squared plus 1. And then what interval are you on? And our interval is from 0 to 2. So I can use this notation now to refer to any right-hand approximation for whatever number of rectangles for whatever function on whatever interval. So that makes it a useful and flexible kind of notation. Notice if we sort of dive into this approximation here a little bit deeper, the height of the first rectangle, by first I mean the one on the left, so I'll count from left to right. The height of the first rectangle is the function value right here at x equals 0.5, right? F of 0.5. And I get the function value by plugging into the function, right? So f of 0.5 is 0.5 squared plus 1, which comes out to be 1.25 or 5/4, right? The height of the second rectangle, so this is the second rectangle right here, is the function value at 1, the right endpoint of the second interval. So that's f of 1, which is 1 squared plus 1. That comes out to be 2, and so forth for the third and the fourth rectangle. Notice that to get the rectangle heights, I'm evaluating the function at certain endpoints of the subintervals. The width of the first rectangle, right there, we're getting rectangle areas here. So all I need for each rectangle is height and width. Well, we've talked about the heights. The width of the first rectangle is 0.5, 0 to 0.5. But of course, a moment's glance shows you that all the rectangles are 0.5 of a unit wide, right? 0.5 to 1, 1 to 1.5, etc. The width of every rectangle is the same. It is 0.5. Okay, so when I compute my areas, I'm going to go width times height plus width times height plus width times height. Here is the first width and the first height. Second width and the second height. Third width, third height. Fourth width, fourth height. And if you plug all this into a calculator, that's where the 5.75 comes from. Okay, so my first hope is that with a little practice, you'll be able to compute things like this. It could be R4 or R5 or R8, or it doesn't really matter what that number is. It could be a different function. It could be a different interval. Lay out your picture, lay out your heights and your width, and do the computation. A little image here to sort of just encourage us that we're on the right track. So this is exactly the same picture from up above. It is just colored a little bit differently, but it's the same function. It is a right approximation. You can see the right button there is highlighted, and there are 4 rectangles. If I increase the number of rectangles, and the magic of a computer is that I can do this really quickly. So here I have, I don't know, a lot of rectangles, 51 rectangles. The thing that I would have you notice is that the area under the rectangles is very close to the area under the curve. So this is promising, right? When we do only a few rectangles, this is what, 5 rectangles, I can see the mistake. I can see where the rectangles kind of stick out and are too big. But if I use a large number of rectangles, they still stick out, but only a tiny, tiny bit. Again, this is promising because we have an approximation scheme, and it looks like we know how to make the approximation scheme better. Okay, let's get back to 4 rectangles. Let's compare this to the left approximation, right? So here's the left approximation. Notice the difference is that now the rectangle tops are drawn using the function value at the left end of the interval. So take, for example, the third rectangle. That's right here, right? 1, 2, 3. The way I get the top of the third rectangle is I use the function value at the left endpoint of the third interval, as opposed to the right endpoint of the third interval, the way this one is. For this particular example, the right endpoint approximation is too big and the left endpoint approximation is too small. That's not universally the case. It depends on what the function looks like. Sometimes you can't even really tell. They're both just different ways of approximating, I think, is the important takeaway. The other thing I'll point out is there's nothing super special about using the right endpoint or the left endpoint. You might say, why not use the point that is, a third of the way through the interval or 70% of the way through the interval or the midpoint of the interval? And indeed, this is what the midpoint approximation looks like. Notice that again, for each rectangle, I use the function value at the midpoint of the interval to draw the rectangle top. We're not super concerned with which one of these is the best approximation, because ultimately we're going to be transitioning from the approximation to the exact value via a limit, but we do want to be aware of how to construct all these different kinds of approximations. All right, let's make this a little bit more general. We've been working mostly with this very specific example, right? A specific function on a specific interval. So let's describe this in a way where we could do it for any function on any interval using any number of rectangles. We'll typically use n to represent the number of rectangles, right? So in the picture here, n is equal to 4. It's the number of subintervals or rectangles. The interval endpoints we'll call A and B typically in the generic case. Okay, sorry for the little gap there, but we're back. More notation for our Riemann sums. We've got the number of rectangles and the interval. We know now that each rectangle is going to have the same width, and we will denote that width by delta x. And notice the way we figure out delta x, right? Go back to the specific example. When n equals 4 here, each rectangle is 1/2 of a unit wide. What about when n equals, let's say, 10? How do I figure out how wide each rectangle is? Well, the entire interval is 2 units long. If there's 10 rectangles, then each rectangle should be 2 divided by 10 units wide. That's the width of the big interval divided by the number of rectangles, or b minus a divided by n, right? So in our example, b is 2 and a is 0. So the numerator there would be 2 minus 0, or 2. Okay. We need a way to keep track of where we're drawing rectangle tops. And we know we can use right endpoints or left endpoints, or really any point in between. We'll call the point we'll use the letter C. So C1 is the point in the first subinterval, C2 in the second subinterval, C3, C4, all the way up to Cn. One point in each subinterval, and it could in theory be any point in the interval, right? So C1 might be the right endpoint of the interval, C2 might be the left endpoint of the interval. In practice, they'll be determined in a very systematic way, but we'll let our notation reflect some generality. We already introduced this notation up above, but this is what it looks like in the abstract. Right, R means we're doing a right endpoint approximation, N is the number of rectangles, F is the function, left endpoint, right endpoint. Okay, and what's next? Yes, of course, the same kind of notation for the left endpoint approximations, except we'll use an L instead of an R for right, and L for left. So in general, the way we get the approximation is we add up all of the rectangle areas. How do I get a rectangle area? Height times width. The width in every case is delta x. So every term in the Riemann sum has a delta x in it. The height is the function evaluated at the evaluation point, which usually is either the right endpoint or the left endpoint of the interval. But in general, it's function at appropriate evaluation point, right? So C1 is the evaluation point in the first subinterval, C2 in the second subinterval, and so forth. So this is sort of a generic form for a Riemann sum. In our example up above, we had n equals 4, right? We used 4 approximating rectangles. The evaluation points we used were right endpoints. So the right endpoint of the first interval was 0.5, and of the second interval was 1, and then 1.5 and 2, and so forth. Delta x is the width of each subinterval. They're all 0.5 units wide, or 1/2 unit wide. And we already know this, right? So I think we actually used that notation up above, and it comes out to be 5.75 because we computed it before. So notice what this means is it means do a Riemann sum approximation to the area under this curve, and the result should be a number, right? It's an estimate of an area, so this should come out to be some sort of number. All right, let's look at a different example. So here I want to compute this thing, and all the words here just express what that blue highlighted thing means in English words. So here we've changed the function. Right now I'm talking about the function y equals 10 minus x squared, and the interval now is from 0 to 3. Here's a picture of the area that we are trying to estimate. All right, so let's go ahead and get started. Delta x is b minus a over n, right? So b is 3, a is 0, n is 4. So we put it all together and you get delta x is 3/4. So each interval is going to be 3/4 of a unit wide. This leads to what's called a partition of the interval, right? So what we're doing here to start is we're taking the big interval and we're cutting it into a bunch of pieces. Each piece has the same width, right? So we start at 0, and then we take a step of 3/4 out to 0.75. And then we take another step of 3/4 out to 1.5, and then another step of 3/4, and we keep going until we get all the way to the end of the interval. So this list of points, right, these are kind of the points we mark off on the x-axis to delineate our rectangles, is called a partition, a little piece of terminology there. So here is a little visual of what that looks like. Here's the interval from 0 to 3, and here are my partition points marked on the interval. And you can see that they divide the interval into 4 equal pieces, and each piece is 3/4 of a unit wide. Okay, so what are our evaluation points? Well, notice back here, this is a right endpoint approximation, and that dictates how we pick the evaluation points. It says you should go to each subinterval and use the right-hand endpoint. So for the first interval between 0 and 0.75, I'm going to use the right endpoint. That's 0.75. That's my C1. For the second interval from 0.75 to 1.5, the right endpoint is 1.5. That's my C2. C3 is 2.25, C4 is 3. And now I can kind of put everything together. The approximation is, we'll keep you in suspense. Right, this was our generic formula, right? F of C1 delta x plus F of C2 delta x plus F of C3 delta x. And I keep going until I get to the last evaluation point. In this case, there are only 4, so I can write out the whole thing without any ellipses or anything like that. I fill in some of the missing pieces. I know delta x is 0.75, right? So all delta x's got replaced by 0.75. There and there and there. And then I fill in the evaluation points. The C1 is 0.75, C2 is 1.5, etc. And of course, F is not an abstraction. F is this function, right? So that's the function that I'm going to use to do these function evaluations. And now this is tedious, but it's just a lot of calculating to figure things out, right? I just have to push a lot of buttons. Here I'm actually showing, I haven't done any of the computation, so you can see where everything is coming from, right? What's the function value at 0.75? Well, the function is y equals 10 minus x squared. So the function value at 0.75 is 10 minus 0.75 squared. And similarly for all the other function values, I'll let you pause the video and check that out if you need to go over it at all. And when I load this whole thing into a calculator, it comes out to be about 17.34 or so, right? So that is my estimate of the area, right? So that is the value of R4. And this blue area, well, it's about 17.3, right? Not exactly, we're still just approximating here. Okay. Let's see what this cell has to offer us. Oh, so this is just the same picture as up above, but for our new example. And we see the same phenomenon. So this is the approximation we just calculated, right? N equals 4. The result comes out to 17.3 or so. If we do a lot of rectangles, we see the same phenomenon where when there's a lot of rectangles, there's very little difference between the rectangle areas and the area under the curve, right? When there's fewer rectangles, you can see that discrepancy a little bit more clearly. So this doesn't prove anything, but it does suggest we're on a promising track here. We at least have a way of generating what look like very good approximations to areas under curves. All right, let's do one more example, and that'll be good for our introduction to Riemann sums. Let's try to compute this thing. Now notice it's the same function and interval that we were just working with. The only thing that's changed here is instead of an R, that's an L. So I'm going to be doing a left-hand approximation. Okay, well, delta x doesn't change, right? Delta x only depends on the interval and the number of rectangles. Whoops, number of rectangles, not how you're choosing the evaluation points. So it's the same partition as before, right? The exact same partition as before. What's going to be different is that when I pick my evaluation points, for the first evaluation point, I'm going to go to that first subinterval, and I'm going to use the left-hand endpoint instead of the right-hand endpoint. Let's see if that's what we do next. Indeed, right? So the left-hand endpoint of the first interval is 0. The left-hand endpoint of the second interval, pardon me, is 0.75. Of the third interval is 1.5, and of the fourth interval is 2.25. So notice we have different evaluation points than what we had before. But now that I have all this, I can build the Riemann sum, and it's the same construction. Again, some suspense. And again, we get this expression, right? This is the exact same expression as before. All that's changed now is the evaluation points are going to be different, which is going to give us a different result, right? So I fill in the things that I know. Delta x is 3/4 or 0.75, right? So all the delta x's get replaced by 0.75. And I've highlighted in pink, I guess that is, the evaluation points, right? So you can see them defined up here. And then they get plugged into the function down here. And again, our function is 10 minus x squared. So these function evaluations are pretty straightforward. When you use that definition of the function, this is what happens, right? F of 0 is 10 minus 0 squared. F of 0.75 is 10 minus 0.75 squared, etc. I throw this whole thing into a calculator, and it comes out to be about 24 and change. And so that's our answer. The problem was to compute this L4 thing, and we say it's 24.09. Notice what we've just computed. Let's reset our number of rectangles in this gadget to 4. And look at the left. So there's the right approximation. That's what we did up here where we got 17.3. When we do the left approximation, notice that now it's the left approximation that's too big. And you can see that on the picture, right? The rectangles are too big with the left approximation and too small with the right approximation. If you're watching closely, you realize that what is driving this is whether the function is decreasing or increasing. Of course, a function could kind of both decrease and increase on the interval, in which case it gets more confusing, which is too big and which is too small. But in these examples, we can clearly tell which estimate is an overestimate and which estimate is an underestimate. And so given this picture, it's not surprising that our computation gave us a bigger number for the left approximation than for the right approximation. Okay, that's good for an introduction to Riemann sums. Take good care of yourselves, folks.